In this lecture, we're going to talk about metamorphic environments. These are specific geologic settings. So by that, I mean a place on Earth and a time. And they're associated with a particular set of pressure and temperature conditions. So from the setting, we can actually know whether there was confining pressure or directed pressure, whether their temperature was high or low. So that's what we mean by a metamorphic environment. We're going to go through all of the metamorphic environments that we're covering, and then we're going to look at with each one, we're going to look at what would happen to parent rocks if they were metamorphosed under those specific conditions. So the first one is called contact metamorphism, and sometimes also thermal. Thermal just means heat, and we use that to refer to contact metamorphism because this is a place where we have a lot of heat, and that heat comes from magma. So this is just an example of a volcano. We've got the surface of the earth and the volcano, and then we've got all the rock here that's surrounding it, and down here we have the magma chamber. So this is hot magma, molten rock. That rock is much hotter, the magma is much hotter than all the surrounding rock. And so that heat affects the rock that surrounds the magma chamber. So this purple area that's sort of lining the outside of the magma chamber, and it's harder to see, but if you look closely, you can see a similar kind of purple area, much thinner, along the pipe that's bringing the magma up toward the surface and having it erupt from the volcano. We call that the metamorphic aureole, or we also sometimes use the word halo. And this rock has been baked. We talk about contact metamorphism baking the rock because we're only increasing the temperature. The pressure stays the same as it was to begin with. So pressure remains constant, but temperature increases a lot because of the heat from that intruding magma. This is the same figure up here at the top, the drawing. This is thousands of years later, right, later in time. The magma has solidified, so this has become an igneous pluton instead of magma, and we can still see the edges all around that pluton where the rock outside the pluton was baked. And this is a photograph showing that same situation. So the white rock down here, this is the pluton that used to be magma. It was emplaced or intruded up into the crust, and all of the rock on top of that, this area here, was baked by that heat and metamorphosed. So remember, that means that it's a different rock now than it was to begin with. So for contact metamorphism, what are the metamorphic conditions? And by conditions, we're talking about what are the pressure and temperature conditions that a rock experiences when it's metamorphosed in this kind of environment. Contact metamorphism takes place fairly close to the surface of the earth in the upper crust. So that's a fairly low pressure environment. It has confining pressure only. So remember, that's equal pressure in all directions. There's no directed pressure. The only time we get directed pressure is when we have some sort of tectonic event like a continental collision. The temperature can range from high to low. Basically, if you think about having your magma down here and then all the surrounding rock around it, the layers that are very close to the magma are going to get very hot, but rocks are not very good conductors of heat. And so therefore, as you move away from the magma, the rocks will not experience the same intense heat, and instead they'll be a little cooler. So we get cooler temperatures of metamorphism here and hotter temperatures of metamorphism very close to the magma. So that's why the temperature can range from high to low. So all of these rocks have been metamorphosed, right, but to different degrees of temperature, and that's going to mean they're going to have different minerals in them. So now we're going to look at an example of what would happen in an area that was experiencing contact metamorphism. So we have our magma chamber down here. So that's the source of heat, and that heat is radiating out into the rocks and baking the rocks around it. So contact metamorphism means that we've got confining pressure only, right? So no directed pressure. So that means no foliated rocks. So we've got a layer of shale here, and we've got a layer of quartz sandstone, layer of limestone, and another layer of shale. So the shale here is getting heated up and is experiencing metamorphism mostly just from that heat and confining pressure. So that will end up giving us the rock hornfels, right? A non-foliated rock that forms from shale. The quartz sandstone also getting heated up. So in this area, that quartz sandstone is going to become a quartzite. As the limestone heats up in this area, it's going to become a marble, and then another layer of shale giving us the hornfels again. One rock that's not on here, which we did talk about, it's a non-foliated rock and it would form in this environment, is the rock skarn. So remember, skarn formed when magma mixed with limestone, and it drove off the carbon dioxide and left a lot of the calcium to mix in with the magma. So the place where we might find some skarn forming is right along the edges here, where we have the layer of limestone, right? And right along the edge, these two might have interacted, and then you might form skarn right there. Another type of metamorphic environment is hydrothermal metamorphism. And hydro just means water, and thermal means heat. So we are talking about chemical changes that are due to hot water. Hot water easily dissolves atoms from rocks, so it tends to have a lot of stuff dissolved in it, a lot of the same elements that we've been talking about, silicon and oxygen and calcium and potassium, things like that. The heat itself comes from nearby magma again, so kind of similar to the contact metamorphism, because that's where our heat comes from. So we have a graphic down here that's showing how this might happen in a situation where we're in the continents, so we're on continental crust. We have a volcano here, but notice that it's dormant. There's no longer active magma feeding it. Our magma chamber down here has been sitting here long enough and not being active that all of this part of the magma up here at the top has begun to crystallize and solidify into a pluton. When that happens, though, the volatile elements, or the gases that were dissolved in the magma, begin to make their way out, and they get excluded basically as the magma turns into rock. And so they penetrate out into all the surrounding rock, creating these veins. These volatiles, these gases, which become liquids, are very hot when they start, but as they move out into this cooler rock, they cool down and the minerals precipitate out into those cracks. And that's how we get hydrothermal vein deposits. And you're seeing some of those veins in this picture of a rock. So these are the veins. The water, the fluids moved through there and deposited crystals as they went. So that's one form of hydrothermal metamorphism. Another place where we find hydrothermal metamorphism is along ocean rifts, mid-ocean rifts, or divergent plate boundaries. In this location, we have a lot of cold water sitting on top of the seafloor. And near a rift, we also have hot magma at depth. right? Because it's basically, you're getting volcanoes coming up through the seafloor, through this rift area right in here, and that's what creates the new seafloor. So we have cold water that sinks down through cracks in the crust, and then it encounters this very hot rock, which is near the magma, and when it does that, it gets warmer and buoyant, and then begins to find its way back up toward the surface. When it does that, as it's moving through the rocks there, it's going to precipitate out minerals in those cracks, just like the previous environment on the continent. So we're going to end up with veins basically being filled with minerals in all of this area that hot water moves back up through. A second thing that happens here is also kind of interesting, and that is that a lot of that hot water actually makes it all the way up to the surface of the seafloor and comes out of the surface like a hot spring. So instead of having a hot spring on the continent where the hot water comes up to the surface and bubbles up into air, this hot water comes up to the surface and bubbles up into the very cold seawater. What happens then are you get these black smokers. They're showing them right here. And those black smokers are actually really mineral-rich waters that are coming up. So again, remember the hot water has been dissolving minerals all along its path along here. So it dissolves minerals. Some of those have been redeposited here in the basaltic ocean crust, but some of them make it all the way up to the surface and become these black smokers. This is a closer look at some of those black smokers. They are both geologically interesting and also biologically interesting. These are areas where you have communities of life on the seafloor, includes shrimp and crabs and these things that are called tube worms here. They all exist by using sulfur, which is dissolved in the seawater, as a source of energy instead of sunlight. So if we take a look at a diagram of a black smoker, we can see the cold water coming down, right? So this is seawater up here, this blue area. And then it reaches this very hot rock down here, heat from the magma below, and that heats the water up. So it begins to dissolve minerals from this part of the seafloor that it's moving through. Then it reaches the seafloor right here, and it comes up just like a hot spring would on the surface of a continent. Only instead of emerging into air, it emerges into that very cold seawater. That causes all of the minerals that had been dissolved in the water during this time, during its travel down here, to come out of solution and form little tiny black particles, and that's what causes what we call black smoke. It's not really smoke, it's those little tiny black particles that are being spewed out as the water comes up to the surface. They also get deposited around the black smoker, around this kind of underwater hot spring, and they form this chimney kind of area right here. So we have a chimney and a black smoker. So back to the ocean floor that's being metamorphosed by that hot water before it actually comes up as a black smoker. So remember that the ocean crust is made of the rock basalt, right? It's erupted by volcanoes. Mafic magma comes up from decompression melting at mid-ocean ridges. That mafic magma erupts and creates the basaltic rocks of the seafloor. Alamine and pyroxene were very important in basaltic rocks, so these two minerals here, two of the main minerals in basalt. During the hydrothermal metamorphism of the seafloor, those are replaced by two different minerals, and what's different about these minerals is that they actually incorporate water into them, so they are hydrous minerals again. So remember we talked about hydrous minerals, anything that has an OH group in it, the end of a mineral formula. So serpentine and talc are two minerals that do have that OH group, so they are hydrous minerals. So we have the basaltic ocean floor gets hydrothermally metamorphosed, and that means that the ocean floor is mostly not made of pristine basalt. It's mostly made of rocks that contain these hydrous minerals, and those include soapstone and serpentinite. So I've got pictures over here of these two rocks. Soapstone contains a lot of talc, and serpentinite, as you might guess from the name, contains a lot of the mineral serpentine. These pictures up here up top are just showing some of that veining, because remember, anytime you get rocks that are hydrothermally metamorphosed, it creates these veins in them. So they're often used, cut and polished, and used as facing stones because of the interesting veins that are in them. The next type of metamorphism is burial metamorphism. Burial metamorphism has fairly simple metamorphic conditions, and it's a fairly simple process. It happens pretty much everywhere on Earth, but especially on the continents. Basically, all you have to do is have about 10 kilometers of sediment build up sitting on top of rocks underneath it, and then that begins to metamorphose those rocks. So that's why we call it burial metamorphism. Rocks at the surface have new layers of sediment deposited on top of them, and that continues to happen. And after a while, they have been covered by 10 kilometers of new rock and new sediment. And that brings them up to that 200 degrees C temperature right there that I kind of crossed out. And remember, that was the lowest temperature at which metamorphism happened. So once you get down to 10 kilometers and 200 degrees C, metamorphism happens. So if you walk around on the crust, the continent of any continent on the planet, you're basically 10 kilometers under you, the rock has all become metamorphosed simply through this burial metamorphism. But this is a pretty low pressure environment in compared to, say, a continental collision. It's confining pressure only, right? There's no directed pressure here, equal pressure in all directions. And we're still at pretty low temperatures. So the metamorphic conditions that the rocks experience as they undergo metamorphism in this area are confining pressure only and fairly low temperatures. Next type of metamorphic environment is subduction zone metamorphism. So this figure has quite a few things going on, but what I really want you to focus on is where this arrow is pointing, okay? We've got a blue oval here and a red square. The red square is telling us basically what kind of conditions the rocks within the blue oval are experiencing. So this is a subduction zone. So remember, we have basically the ocean lithosphere subducting underneath a continental plate here. Rock, again, is not a good conductor of heat. And so the rock up here is pretty cold. As you transport it down, it takes it a long time to warm up. So what we find is that the rock stays at low temperatures, but we're forcing it very deep into the mantle of the earth. And so those low temperatures are combined with very high pressures. That's an unusual environment. It only occurs here in subduction zones. So low temperature, high pressure. And one other thing to remember about this is a place where we have directed pressure. This is a continental collision. So one continent, this one is moving in this way, right? And this continent is moving in this way. And so therefore, we have more pressure in that direction than we do in other directions. So the rocks that are made here are going to be foliated, because that's what happens to metamorphic rocks when they form under directed pressure. Here are some examples of the rocks that you find in this environment. When we talked about foliated metamorphic rocks before, the parent rocks we talked about were mostly sedimentary rocks like shale. So these rocks were formed from an igneous rock. So that's different from the other rocks that we've talked about. And that means that the rocks themselves are going to be slightly different too, because they're going to have different minerals in them than the shale did. So the rocks that form are blue schist and green schist, and so they're both schists, right? So that means they have both been metamorphosed to a pretty high degree. They are foliated, schist is a foliated rock, and has a fairly large crystal size. You can see how they got their names. These are pictures. We have the blue schists up here and the green schists down here. They have some very dominating minerals of those colors, and that's why they put the word blue and green in front of the word schist to name these rocks. Then we get to regional metamorphism. Regional gets its name because this type of metamorphism basically is taking place over a very large area. So this happens when two continents collide, right? So regional metamorphism is when two continents collide. We talked about this when we talked about plate tectonics in general in Chapter 2. That was a collision zone as opposed to a subduction zone. Neither continent will subduct because both of them are too buoyant. That this happens after subduction has removed an ocean between two continents. So we can see down here the remainder of the ocean floor that used to be between these two continents and was completely subducted until the two continents hit each other. So we have directed pressure, right, those two continents coming toward each other. So that means that we're going to have foliation. We have a range of high to low pressure and a range of temperatures, and that's because this is such a huge area that's experiencing metamorphism. So in the center area, around here, you have very high temperatures and very high pressures. But when you get out towards the edges, the temperatures and pressures are less. So it's all still foliated, it's all still part of this regional metamorphic environment. So it all is experiencing directed pressure, but some of it is going to be higher pressure and temperature than other areas of it. This shows the rocks that we have talked about in terms of where they would form within this regional metamorphic environment. So again, we've gone back to the foliated rocks that would form from the rock shale. So if you could follow a layer of shale within this area of deformed rocks that is formed when the two continents collided, you would see that out here on the edges, it's experienced rather low temperatures and pressures, and so that gives us the rock slate. As you keep going in, so now we're a little deeper, right? There's more mountain on top of us, there's more heat. We've got the rock phyllite forming. So the grain size of the micas in slate has grown a bit bigger because of the additional heat. Then when we get down here into the roots of the mountains, where we're really deep, and we have much higher temperatures, we end up making schists and gneisses as the rocks there. So if you ever go to an area, Ontario is a good area up in Canada, there are a lot of schists and gneisses that you can walk around on, see at the surface of the earth. What that means is that those rocks actually were formed very deep in the crust at the base of a big mountain chain. And then the rest of the mountains got completely eroded away, and now you're walking on those rocks that were formed at such a deep level. So I wanted to end with this slide because it's a graph that you're going to be using in one of your lab assignments. So we've got our 0, 0 here. We've got temperature increasing in this direction, and we've got pressure increasing down this direction, along with, on the other side, the equivalent depth into the crust of the Earth. What you're seeing here are the temperature and pressure conditions that we've talked about in the previous slides put onto a graph. So for instance, subduction zone metamorphism, which is down here in this kind of greenish blue area, this gray arrow is indicating the direction in which pressure and temperature change during subduction zone metamorphism. So as a subducted slab is pushed deeper and deeper into the mantle of the Earth, we find that the pressure increases quite a bit, right? We start at this pressure up here, and by the time we're finished, we're down at this pressure here. So we have got quite an increase in pressure. Temperature, on the other hand, starts right about up here, yeah, and ends here. So we could draw the arrow for temperature as well. And what we find is that the pressure has actually increased faster than the temperature has increased. And that makes sense with what we talked about with that environment, how the rocks stay cold even though they're pushed down into the mantle. They stay cold for a long time. It takes a long time for them to heat up. We could also look at contact metamorphism, that's up here in the red. So contact metamorphism was the one where you have a magma intrude into the crust and it kind of bakes all the rocks that it comes into contact with. So we can see that baking in the temperature increase in contact metamorphism. But notice that the pressure doesn't change. The pressure, which is measured over here, is exactly the same here as it is here. So even though the temperature has increased a lot, the pressure hasn't changed at all. So we can just see how those conditions are changing when we look at this graph.